Um, welcome everyone to our quantum formalism fireside chat Polyadic quantum machine learning. Our guest speaker Joaquín Keller, um, who um, has co-founded Anthropica Labs and now working exeq.ai that is focused on quantum machine learning, and he has completed his MS in theoretical computer science and PhD in distributed algorithms. Yakin is mathematician and he has taught various university in Paris based and worked in research teams in R&D division in French global telecommunication company. And me, I will be your host, Sakibul Islam, and the floor is to Yakin. Let's start.
So hello everyone, and thanks for having me. Um, so I'll be talking tomorrow about this machine learning algorithm that we named it a Polyadic quantum classifier. Polyadic just means multi-class in Greek. And so this paper, I wrote this paper that was peer reviewed and presented at this IEEE conference with two interns uh, that had no prior knowledge of quantum computing. I just saying that for the audience to know that this is not something you don't need necessarily a PhD to do this kind of work. Quantum computing is for everyone. You need maybe some mathematical basis, but not necessarily physics. So let's go and start first with a bit of context. We tend to say that we are in the NISQ era, and that the quantum computers are not very powerful. That maybe in a decade, a quantum computer would be powerful enough to do interesting things, and so. But actually, so it's true we're going to have many qubits and we have a higher rate, and but we're having more and more qubits. I would say it's more that we are in the era of quantum supremacy, because actually, it was more than 1 year ago, Google did this experiment with the quantum supremacy experiment, and they ran some algorithm, some problem that would have taken 10,000 years with a classical, with the supercomputer, would have taken 10,000 years, but with their Sycamore, prototype, quantum computer prototype, it took only 200 seconds. So actually, we are now in the era of quantum supremacy. This is like a threshold that we have gone. So quantum computers are actually powerful enough. So the problem is not that we don't have the computer. The thing is that we don't have the software. So the question is, where is the software? So what I mean by that is that we can now try to have software that run on today's computer, and maybe that have like quantum advantage. This is something doable. This is something that will happen in any moment. Someone will come up with something that will run faster and will be useful. This could happen today. It could be one of you there in the audience that will do that. So here, in the NISQ, one of the best candidates is exactly it's machine learning. A lot of people just say, John Preskill, when he defined the term NISQ, just say machine learning could be a good thing to run on these first computers. And then you have like Zapata or Cambridge Quantum Computing or other companies that they are doing machine learning and raising this huge amount of money for doing that. Google is claiming they're doing quantum machine learning. IBM recently announced that they were doing quantum machine learning just like now. So this is something that is a hot topic, and raising a lot of interest and a lot of money. So, but actually, I mean, when I started working on quantum machine learning, maybe it was 2 years ago or something like that. And actually, I was surprised that there were almost nothing running. I mean, you had like papers saying we could have something, maybe we could do it like this, or there was something running on simulator, but no, there was nothing running really on the computers. There are not even a simple problem. So, I mean, usually when you have like this, I mean, a quantum algorithm, it's running on something on where if you are a beginner, say in machine learning, you try a lib, you try something, and you do some kind of first simple problem. Usually, it would be the iris data set, and and you run it to see if it works. If you have understood how the algorithm works, I mean, it's like what do you kind of example that we say the hello world. Example, the thing like, I mean, you just want at least to print hello, I mean, to see if your stuff is working. So this is what I try to do, and actually it works. So this paper that it was in, I mean, we did we ran it. It was maybe in April last year, less than 1 year ago. And we did the full problem, a simple problem, that was the training, or training the network, I mean the quantum model, and the testing, everything on real QPU, on an actual hardware. It was an IBM Q. And we did I mean, the full problem, multi-class, I mean, on this iris flower data set. That is a data set that is simple, but I mean, not trivial, complex enough, so you cannot do it just like without a computer. You need a computer to do it, but it's still quite small and simple. It's typically what you call but I mean, if you are not able to run iris, as I said, you have nothing. So now we have something. We have this this algorithm that so we did it, we ran it on IBM Q. We get the same accuracy at a classical ML. We tried it with other data sets. So that means the algorithm, I mean, is working. And we have this answer to the question, can quantum machine learning run on today's quantum computer? Yes. So this is a very good point. Do we have, I mean, some advantage of running that on quantum computer? Probably not for these small problems, but yeah, it might be. We're not sure. This is an ongoing work. So let's. I'm going to go and explain how this algorithm works and general. So let's go first a little bit back and go on the basis. So if you look at a quantum computation or a quantum computer, you just you input some a circuit that is a program, a series of gates. You say how many shots you want, how many times you want to run that, and you give that to the quantum computer, and you get a list of bit string. It's what you measure there. I mean, the measures of the qubits. So you get the bit string corresponding to these measures. So this is how a quantum computer works. There is something that you can see there. I mean, if you compare with the classical computation, is that there is no data. There is only the program. I mean, in the von Neumann architecture, you have the program and you have the data, and then your program runs and look at the data and keep going. This is nothing. So you have to put all the data has to be in the program, every data that you put to run the input data has to be inside the circuit. So this is like basic. You cannot do it. You have to do it this way. So for any kind of problem, and it's not specific to machine learning. So how to do that? So we take you have the circuit can be parametric. I mean the parameters are 2 pi periodic. So we call them rotations, and um, and so the circuit can have these parameters. So we take a parametric circuit, that any circuit actually it's parametric. You're gonna say they have some parameters, maybe fixed parameters, but they have the parameters, and then some of the parameters you are going to call them the input parameters and call it omega parameters, and the other one are going to be the model parameters. The model parameters are the parameters you want to learn. So your algorithm. I mean, this is the one that you want to find the right theta vector of parameters to have your input. So what you do is that you take your input vector, the data is your input, you encoded it into angles. So that means you take, like in this case, we take each of the values, like from x min to x max, and we converted it an angle, omega min to omega max, and so this just by a linear uh, scaling. So if you have questions, I mean, in between, I accept question in the middle. So maybe we can send a question.
Yakin, I have one questions. Can you please explain how can we define that this category is classical machine learning and this is quantum machine learning? And another supplementary question: as long as we are in the era of NISC,
Yeah.
so what are the criteria that should be followed to work on quantum machine learning datasets on NISC based computation or quantum computer architecture?
Actually, at the end of this presentation, I will come specifically on this idea of how to prove, I mean, quantum advantage in the specific case of machine learning, and how we can do that. I mean, I've been thinking this was my first problem of how we can do that. So I will go on that part. And I don't know. I don't. Can you repeat the first question? Because I'm not sure I understood. Uh,
Sure. First question was how can we categorize this one is classical machine learning, this one is quantum machine learning, or you can interpret the question like this: what are the characteristics that should be followed to be it in classical machine learning or it in quantum machine learning? I
I
mean,
would
what are the
say,
separation?
okay, yeah, exactly. So quantum machine learning, I'd say quantum machine learning in the what I would define here in quantum machine learning is when there is some quantum computation in the model. The model, I mean, for people that know machine learning, you have a model and you want to train the model. So the model, or for example, it's a predictor that just kind of you want to predict a function. Here it's a classification, and so the predictor has to have some quantum computation in it. And when it's that, it's you can say it's a quantum machine learning. When the predictor, when the model is quantum, I mean it has some quantum computation in it. So if it's the case, it would be quantum machine learning. I don't know a better definition. This one is the quite general one. If you are, it's something like say, if you are using a quantum computer to come up with your results, it's a quantum machine learning. It's just machine learning, but with quantum computers. So actually, I just like there's no more difference than that. So that's why I'm just like in the title of my new company, Exaqui, I just put oh, I see in the chat, the predictor result is theta. I'm going to go on that. Let me continue on the technical one. So I'm going to, maybe they will going to have a lot of answers on that. So here to encode the theta is the result of the learning. But I mean, let's go on that. So to encode the value, you just encode it in angles. For example, if your x values are, let's say, between 0 and 10, to say something, you are going to encode that in an angle between 0 and 2 pi. Actually, you add a gap to be sure that 0 is not equal to 10, because 0 and 2 pi are the same. I mean, for an angle are the same stuff. So you put it some distance. So this is very simple. Each value of your, each value of your vector is just encoded there. There might be other ways of encoding. A vector of x values in a vector on omega on a vector of angles. But this is the way that we did here, a very simple one. So if your vector has a dimension, x vector has a dimension of n, the omega will have the same dimension in that case. But you can figure out other ways to encoding this function. So you do that, and then you have, for example, for the iris data flower, this is like the quantum circuit. So I assume that people here in the audience know a bit about quantum computing. They know what is a quantum circuit. So this is the circuit so the entangling gates here are CZs, and so this is the circuit. And so you just put the sepal width and length, petal length, and width on the omegas angles on these rotations here. So you rotate so how do you get the results here? So you put your angles, you rotate the qubits by the value. I mean, if the sepal length is that, you rotate it by this length, and etc. You rotate that, and then at the end you get zeros and one. You get some results, no? And so the result you want to be that this is going to be the predictor. So this is the predictor. This is the one that gives you the answer. And here, what you want to find, the learning part, is to find the thetas, the right thetas. So when you measure, you get the right answer. I mean, the class. I mean, the right class is, you have three classes: setosa, virginica, and versicolor. And you want the answer to be right for the given theta. So here, how do we, put the predictor is that if the circuit, when we run it several shots, if you run it only once, you get like one random result, but you have an underlying distribution, so you run it several times, you have a certain number of shots, and if the most frequent outcome is 0, 0, both qubits are at 0, for example, in this case, for setosa, for the iris flower data set, it will be a setosa. If the most common result is 1, 0, it would be virginica. If the most common one, it's 0, 1, it's versicolor. So that's why now you want to find the theta that gives you the right answer. So if you put that formally, like it's the predictor, that is y hat, that is standard notation in machine learning. So the predictor is what I was saying, like more clearly than maybe like reading the formula, but this is the formula. It's the most frequent bit string that determines which class is it, and to each bit string, to each class you associate a bit string. And so if this is the bit string that comes more frequently, this would be like the right answer. So you see, this predictor has a parameter in theta. It has also, sure, it takes as an input, it takes x, that is the vector that you want to classify, and so the learning process is to find the good theta star that you got a prediction that is accurate enough accurate to be useful. And for doing so, you compute a loss function, and that is like a loss function is the loss is or it's called the error. It's how many you have wrong, and you want to minimize this loss. You want to minimize the loss. So you want to find the theta star that minimizes the loss. It could be a minimum that is good enough, so your prediction is good enough. And so if you look at the loss, This is the loss for 1 point. You see how much so this loss function is called cross entropy. It's a classical one in machine learning. And but actually you're not going to minimize. You are going to minimize what you want to minimize is the average. So you are going to minimize the average of all this. So you compute for each data point. You have to compute the loss for each data point. So you input one x, you get the some predictor, the output, and you compare. If it's not good, I mean, you just got a big loss. And then you add all that, and this is what you want to minimize. And what is interesting, and this is what give me, I mean, I have hopes to reach some advantage here, is that when you, I mean, you want to minimize a function. This function is quantum, so that means it's stochastic. So that means that each time you run it, you get a different result. And so how can you more minimize a function that changes values? I mean, each time you make the call, even with the same input. So actually, that's why when we do the shots, because we do the shots, and at some point it's an average, and you got something that is stable. No? So because you are averaging your output over many shots. So at some point, I mean, you get you get a stable function enough to get it minimize it. But here, actually, since you are averaging, uh, because you have many data points, you are averaging all the data points. This is the sigma that you have there. It's the sum over all the data points that you get there. So you're already doing an average. So you need a lot less shots to get something stable, to be able to minimize it. And why so? Because actually all the data points are quite similar. That's why you learn. I mean, if you have two cats, they look like cats both. So if you want to classify cats, when you run one, you run on one data point, and then you run to another data point, and they're quite similar. So the distribution for this circuit and for the other circuits, is the both circuits are very similar. So you don't need actually when you try it empirically, because it is dependent on the structure of the data set. You see that you don't need many shots. Actually, surprisingly, you can do things that work, that learns with something as small as 10 shots per circuit. This seems like uncanny. I mean, it was just, I was so surprised. Actually, it was William that the intern was working with, just, I mean, he was like a noob. I mean, he's doing a master degree in mathematics. He didn't know about quantum computing, about shots, about things. So he was just like trying things. And he just tried with 10 shots to see what was going on. And it worked. So we were, I mean, puzzled, what's that? I mean, usually people just say you need thousands of shots. How can it's possible that you run 10 shots per circuit? It was working. And this is the explanation. This is the explanation of why we need 2 shots. And that's why we were able to run the whole algorithm on today's quantum computer, because we need very little shots in total. So we were able to run this many circuits that we needed to do the learning. Because the learning, I mean, how you do the learning? You started with some set of parameters, and then you compute for each of the data points. You run a circuit. So if you have here, I mean, the data set is quite small, but you still have I mean, we had 90 points on the training set, and so we need to run 90 circuits, and then you I mean, compute the average, and then you see how good is the result, and then you take another set of parameters and you start it again. So each time, each iteration, you need at least to run 90 circuits, and probably even more if you do gradient-based I mean, optimization, because each gradient needs to run again a circuit, so you need to run 90 circuits multiplied by the number of parameters. So this is a huge amount of circuits that run. So, but you don't need many shots, so that's why we're able to run all these circuits. So I think there is maybe you have a question there. Oh, it's okay. So I keep going. Um, Okay, so this presentation was meant for something longer, so I'm going to skip I'm going to skip some slides. So here it's so we went on this data set. So this is the iris flower data set, the one I was talking. So but with the circuit, the parameters, the thing, and here this is like we ran it also with the skin segmentation data set, a very known data set that is used for doing to find the people in skin in pictures to do segmentation. And this is a mobile. So for a mobile, you need to have a circuit, a mapping of the data on the circuit, and how do you map the output on the thing. So this is what is a quantum model. So this is like another data set with the corresponding model, and another data set, a synthetic one with another. So this is the model that on the paper we did it. So for the iris flower data set, we ran it on 1 hour and a half, the whole training, and we got the same accuracy that the classical one. So this was in that moment in April. Since then, we're able to run it others with good results as well. So here the question, it's okay to run machine learning on today's quantum computers, and I think that this paper was the first case, but the people would say, yeah, but it was a small problem. It didn't show anything. It's okay. It still was running. So, but actually, how do you can show quantum advantage? If you have like Shor's algorithm, you can do the quantum advantage like a kind of theoretical result, and to show that you will have quantum advantage for this one, even if you cannot run the Shor's algorithm on today's quantum computer, at least not for big, for significant numbers. So, how is in general the quantum advantage? You have to show first that the result of the algorithm is correct, what the algorithm that you have run on your quantum computer, it has the result is okay. And the other one is that it was better somehow. Usually you look at the speed, the time complexity, but it could be space complexity, or people that just talk about energy, that is need less energy, and you have to show that it's better in somehow. So this is for every algorithm you want to show a quantum advantage, you have to do that. You have the correctness criteria and the complexity criteria. And this is the thing. So in the case, if you look at the specific case of machine learning, there are two processes actually. So first, you have this learning process. Then you put a data set, you run the learning algorithm, and you end up with a trained model. You end up with a predictor. Meaning you end up you find the theta parameter, the theta star, the one that gives you the right answer. So you got the trained model. So this one has to be correct, this first process, meaning that you have a trained model that it gives you a good answer. So the trained model has to be correct as well. In the thing, and now but for the so that means that to verify, first you need to verify the correctness criterion. So that means in case of machine learning, you have to run the learning process. You cannot show that your algorithm is going to work with any kind of data set, and it won't run for any kind of data sets. It runs with some data sets. You want to run it to be able to run it with useful data sets. So that's why you have like a data set for, you have the standard data set, your data sets. These are the useful ones. So you need to run the learning process with some data set, at least some, and usually several data sets. So this shows that your algorithm is good. Your learning algorithm works. So this is what we did. We ran it for some data set, and it works. So we have the correctness criterion for these data sets. It's not like the algorithm is going to work for all data sets. Actually, for the moment, we haven't been able to run this algorithm with big data sets. It doesn't mean that it's never going to work. We weren't able to run it yet. So we haven't showed the correctness criterion for big data sets, but we have it show it for small data sets. Yeah, I see the question here in the chat that say that data sets are made for classical algorithms, but a data set is a data set. You want to learn the predictor. If your predictor is quantum or not quantum, the answer would be the same. I mean, if you have a picture that is a cat and a picture that is a dog, your algorithm has to be, it will say that it's a dog or a cat. It's not classical or not classical. There is no, they are not intended for, it's machine learning. The machine learning could be with a quantum computer or not with a quantum computer, with a GPU or TPU, it's the same. So this is for the correctness. But now we have this other one. This is like the complexity criteria. That means is your algorithm, your quantum algorithm, either the learning process or the trained model, the predictor, is it running faster than the classical one, or maybe both? I mean, are faster. How faster they are. This is the question. So here, I would say so. This is that you have to show that you have to show that you have this learning process. It's better. So that is faster. So either for the learning process or the predictor or both. Actually, it's more interesting for the learning process because this is the one that takes a lot of computation. The predictor usually at the end, the trained model is something faster. So you want actually to have like the learning process to be faster. So how we are going to do that? How we are going to do that? So we imagine this is the roadmap. You get some money from an investor, and you want to go and to try to find a quantum advantage with machine learning. So how we can do that? Since you need to ensure the correctness criteria, you have to run things on data set. You have to run it. You have to train it. You can a theoretical result would say, if my algorithm works, it would have quantum advantage. But I mean, how do you show it works? You have to put your data set and run it. You cannot have a theoretical kind of result. You really have to run your data set. And then, I mean, when you have run it, then you look at the complexity, and you see if it's doing better. And so the way of doing that is I will try with some data set, trying to do my best. I will see if this best is better than classical machine learning, and I will repeat that at some point. I find quantum advantage. Actually, this will give something like this curve. So the green one is what you will have like for the learning process when you do this learning. I mean, there are the learning usual algorithms on the problem size. I mean, you can measure the problem size on the number of data points or the size, the number of, the dimension of the input vector. This is usually how do you measure a problem size. And the classical ML algorithms, they are on x cube problem. So quantum advantage would be like the blue or orange curve. It would be like, for example, that you have like exponential speed up. Is that I mean, actually, you add more uh, the, the you add more points. So I have this question that is interesting. How long did it take to build the quantum model for the iris classifier? So actually, they were like to design the quantum model. Actually, we just like try circuits. They're a bit at random. We don't know yet how to do like the good models. I had this idea. We tried things. It was working very well, but at some point it worked. I mean, but it was like it took like one day tweaking things. I mean, trying to find things, and then we run the algorithm, and it worked. We find it. Now, this is another way of asking the question: how long it takes to train the quantum model to get there? I mean, on the simulator, it's only 2 qubits, so a simulator is quite fast. So it takes like, I mean, I don't know, 1 second maybe on my laptop. But actually, on the actual quantum computer, it takes like more than 1 hour to train. I mean, maybe we can improve that, but now it took less than 1 hour using a Kobila optimizer. It might be that we could improve that, but this gives you another magnitude. But just because, I mean, the quantum computer are not so fast. But imagine that you had something running with, let's say, 30 qubits. I mean, my laptop, 30 qubits, I don't think my laptop could run 30 qubits. I mean, I don't have enough RAM for that. They can simulate 30 qubits. So and 30 qubits on a quantum computer, I mean, it's a lot faster than a 30 qubit simulated. And if you, I mean, on a small machine. And if you go on the realm of 50 qubits, I mean, no way your simulated stuff could work. So you really have to run it on a quantum computer. But it's more like if you compare now how long it takes to do the problem like the iris data set, or even, I mean, this takes like a few seconds. But if you look like the latest super cool algorithm, I mean, learning algorithms that we have there, for example, the GPT-3 from OpenAI, that, I mean, you have like this model seems like to chat like or to write text like a human. I mean, it's like it's beating the Turing test. I mean, or maybe making irrelevant the Turing test. And this one was running like many. I mean, it needed many weeks, or I mean, many processors running that. I mean, on the realm of, I mean, it was like a huge problem. So you have the biggest problem needs several weeks to run. For example, again about OpenAI, they have teamed up with Microsoft to use a supercomputer to train their models, because they need a huge amount of compute power that's running for several days or weeks to train a model. And this is how it would be super cool. So this is the green curve that grows, and for the problems. And if we could have something that is a kind of exponential speed up, the meaning instead of needing 1 week to train something, it could maybe we could train it in 1 day or maybe 1 minute. But it would be more impressive with something that you cannot even think of training it, because it's going to take 10 years to training it. Maybe it would be something doable in 1 week in your quantum computer. So this will be like really incredible if I mean, if we could manage to do that. And this is the dream, and this is why we have seen these huge investments in quantum machine learning, because I mean, if we could do that, it would be just, I mean, incredible and super valuable. And this is a kind of a dream worth pursuit, and that's why I invite you, if you want to join, let's say, the quest of quantum advantage for machine learning. So a good starting point will be to go on the website of Exequai. You have there the whole the data, the repository. So you have the code, you can run the code, modify the code, do what you want. So I mean, how you could contribute to that? So now I mean we can talk of real contribution. I mean, at first you just, take the repo there and you can run it just like the example to start with. The iris data set, you run it on your own. And then you try another data set. Maybe you try your own parametric sequence. You see what's going on. You can go inside the code and say, no, the predictor that you made is one with argmax something. I mean, it's not, this is, maybe we could try another predictor, or maybe the loss function, this one is not easy to optimize. Maybe we can try another loss function. We can try or also other optimizing methods or functions. So I'm here. You can send me an email for any question that you have, any help, or if you want just to have an exchange to collaborate. I mean, I would be happy to go on that. Let me see if I here can go on wait a moment. Questions? Okay, here, perfect. And so this is the link. My idea was to drive you. Maybe I mean we can go on the question, but I mean I can go meanwhile. I can. Yeah, I think it's better. Just go on the question. You can browse the exaquire.ai. You will find the code. Okay, let me. I think it might be a good idea to just move to there. Let me see. I can go. I'm going to move here. Yep. And there. How I can share. Wait a moment. I'm trying to figure out how to share something else.
I think you have to stop sharing the current.
Yeah. This is what I understood finally how to get there. So here I'm sharing what you see on the
Yeah, we see the repository. I mean the page.
Yeah, the page. Yeah, the page. Yeah. So this is it. So here here's the this page. So here, this is the experiment I was talking about. You don't see my mouse here, okay? This is the experiment that I was talking about here. So you can go. There is a video here where I explain the whole. Where I explain the experiment. This is just talking about the experiment on the Iris dataset. How it went there, and here, so this one I recommend you. This one is very easy. It's even for non-technical person can understanding it. Here you're gonna have like all the statistical data. Here you can run the experiment and you see how the probabilities grow. Let me see here how the probability associated with which one when the bit by bit they're learning, and you see how the secret learns and improves its accuracy while finding the parameters. And at the end, I mean, when you present a red point, you get the red. I mean, a setosa, you get the red output. So bit by bit, your surface learning. Okay, so here you have like you see the parameters how they're learning. So and I keep going and showing you what is on this page. So here you have like the paper. You can grab the paper here, and the one I was talking there. And here you have the you can just like go and GitHub this one and git you can clone it, git clone and do your test. And yeah, this you can run it on the on Qiskit, or you can use this simulator. The simulator I wrote that is particularly fast for doing machine learning, because it ran in parallel many quantum registers up to 1,000 or things like that, a quantum register in parallel, and make it a lot faster to train, to try things. So this is like when you do pip install, when you pip install the Polyadic library here, when you pip install, it just go, you need it install as well, I think Manicube. And oh yeah, this one is kind of funny. This one is an early version. When I started doing that, I was trying, but it gives you an idea what's going on behind the scenes. So here you have the parameters theta, and you can, and there is only two omega, omega 0 and omega 1 here. And this is for another problem that is, but you can change the parameters in a way that it's that it changed. So you have here 4 parameters, because the quantum circuit here have 4 thetas, and you can change these thetas to make it then match the data points, that is blue and orange dots. And so when you do the learning, finding the best one is going to do, for example, this one, and then you have this and you have an accuracy that is quite good for this data set. Oh, the screen is not updating. Oh, sorry, I've been like talking without you seeing anything. It didn't work. So sorry about
Yakin,
that.
I have some questions related to your works that I have been following or just researched. I think in your just the mentioned paper, you have worked on maybe more than one IBM quantum computer. Am I right?
Yeah, actually, to speed up things, we were able. I mean, we do the training on only one, but then we tested if the model that was trained on one quantum computer, it worked with another one. Because I mean, it's like this idea that they are different, one computer to another. They have different error patterns. Maybe they have cross-talking between the qubits and things like that. So we were thinking, if we would train on one quantum computer, if we run another quantum computer, it is still working. And it did. I mean, it did work. And we also, I mean, we can try to run in parallel. So we have like several quantum computers. I mean, this one, the IBM have like 5 instances of these 5 qubit machines. So we were able to run in parallel and the different machine, and to do the training using several quantum computers at once. As well, since we were needing only 2 qubits and we have 5 qubits, we were using on the with 2 qubits and 2 qubits on the machine, 1 qubit unused, and we were running. When we had the circuit, actually the circuit has 2 circuits, because we were using, I mean, 2 qubits that they were 2 qubits and 2 qubits that they were not entangled, the one with the others. So we were doing parallelism within the quantum computers as well, to speed up things. Yeah, this is another reason we just were able to fit it in small amount of time, because we did that in parallel.
Yeah, I think that means did you did anything error mitigation or error correction?
No, there were no error mitigation. This was just like it was. It was. I mean, error.
I think you were working on NISC device, so
yeah, NIST
as
device.
long as
Yeah,
you
yeah.
are that it should be error correction, if I'm not wrong.
No,
And
no, I
I
didn't.
just
I didn't. I mean, you have the algorithms that run on NISQ. I mean, you have the quantum supremacy. I mean, experiment, you don't need a row correction. And this one didn't need a row correction. I mean, it just like worked. I mean, you just take the output of the qubits. They're more frequent. If they're 0, 0, I mean, it's more frequent. I mean, it's a setosa. You don't need more. I mean, why you need a row correction? I mean, the accuracy was good without. We don't need. Yeah, don't need it.
Can you share, please share the man? Can you please tell what was the accuracy percentage was there?
What was the question?
Accuracy rate.
Huh?
Accuracy rate.
Okay.
Accuracy rate. What was the accuracy rate in iris flower classification?
Oh yeah.
I want the basically I'm trying to say what is the accuracy result.
Oh, the accuracy,
you just...
the same as the classical one. The accuracy, I mean, it was 95% or something like that. This is the accuracy that you have like the classical algorithms, because actually it's a small number of data sets. So, I mean, if you have like 1 point less or on the test data set, the test data set we were using 60 data points. So if you miss 1 point, I mean, you just lose like 2%. And so we had the same accuracy that was around 95%. But what I'm meaning is that due to the small number of data points, you cannot get 100% because, I mean, the precision given the size of the test data set is too small. So we had actually the same accuracy as the classical ML. Same accuracy. We had 3 classes. We separate the 3 classes. Not only the easy one that you have the setosa that is very different than the 2 different ones, but the 2 others are just like mingle like this. And so you have to separate them. They are not linearly separable, to take the technical term. You cannot separate them with a simple plane. And but it did work. I mean, it was the same iris problem that the one running with the male, and we get the same results. And,
cool. Yeah. There is one question from audience. If I'm not wrong, he is Francisco. He's telling how your framework can be implemented on Xanadu Pennyline for comparison of QML classification.
No, actually, Xanadu Pennyline, I mean, they're having a different algorithm. They're running a different algorithm. So it cannot be implemented on Xanadu Pennyline because it's a different algorithm. So, I mean, you can run it on some quantum computer, but Xanadu Pennyline is not a quantum computer. Xanadu Pennyline have an algorithm that is different. It's not the same algorithm. They use actually amplitude encoding, and amplitude encoding is not possible to run on a real computer because to write on the amplitudes, you need 2 exponential n operations. So actually, Pennyline can only run on a simulator. You cannot run it on actual computer. It's not going to work. So it's not universal machine learning. It's their algorithm is like this, and the encoding is not like the encoding I was proposing. The encoding is amplitude encoding, and this one is, let's say, parametric encoding. So it's not you cannot run. And by the way, I mean, I don't think that you could run using Xanadu Pennyline the iris data set on a quantum computer. It's not going to happen, but I'm not even sure you can run it on a simulator. I'm not sure it's doing something. It's only doing like binary classification, and this one you have like it's ternary classification. You have 3 classes and separated at once. Pennyline, Xanadu Pennyline is only doing binary classification, so you can only classify 2. So, and I'm not sure. I haven't. I mean, I'm not. I haven't tried to do that. It should work. I mean, it should work. It should work, but not on an actual, not on a QPU, only on simulator, because of the amplitude encoding. That is almost. I mean, that is not possible to do on NISQ machines, at least. Not possible. We have too many you need 2 exponential n operations to do the amplitude encoding, and and by the way, if you need 2 exponential n operation to encode your data in, it defeats the thing. You cannot have quantum advantage because you already spend all your budget in 2 exponential gates just to write the data. So that means it's not going to work. So the question say, how many different classes did I have in the data set with more classes that you tried? We tried with 4 classes and it worked, but I mean, we don't see any limitation on the number of classes. Right now, I'm working on MNIST. I want to do 10 classes. I do have some results. I mean, I haven't yet showed the result because they are not as good as the classical MNIST. That is, I want to have at least 90% accuracy to be good, but they are a lot better than just random. So it did done. Yeah, so the same question by Francisco. They say, do you use Qiskit inside your framework? And actually, no, we don't need Qiskit. But when you want to run it on top of some computers, I mean, Qiskit is used by IBM and Honeywell, at least, maybe others. So there is you can run it on top of Qiskit, either simulation or actual hardware. Oh yeah, I see someone trying to do fashion MNIST with Qiskit. This one is a hard one. Yeah, so yeah, it could be. I mean, I think that they have an interesting data set. Could be as well CFAR. That is the one with images, and yeah. So yeah, this is something. I mean, it would be very interesting. So I just I see like on the chat Francisco Perez Zorro. That I mean, I can tell him that he can. Send me an email. I would be really happy to answer. By the way, my native language is Spanish, so hola, Francisco. So just for I have a French accent when I speak, so sorry about that. But my native language is Spanish. And so maybe you have other question out there, or I mean, we are nearing 1 hour. This is to Francisco say he will try the framework. So yeah, I encourage people to try the framework. I don't know if we have if we have other question out there. Yeah.
I have not got any other questions from audience. From my side, I have just one last questions that is related to class verification, and just simple generic question: is there any relationship with the increment of class that will classification with qubit? That means if I say there are 4 classification, then I have to use 2 qubit or 4 qubit. If I say there are 16 classification for my data set, and there will be 16 or 32 qubit, is there any kind of relationship for qubit and classification?
Actually, I mean, it's something that we don't know yet exactly how to choose the circuit given the problem. But I mean, if you I mean, I don't know. For the moment, we have tried things with a small number of qubits, and sure, if you have like for this algorithm specifically, if you have only 2 qubits, you can go up to 4 classes. But if you 3 qubits, you can go 8 classes, and so on. So that means that if you have like 10 qubits, you have 1,000 classes. Usually, classification doesn't go that high, so the thing is that for bigger, for data, more dimension or more classes or more qubits, but using more qubits, maybe this algorithm is not exactly adequate because we don't know exactly how to design the quantum model. So the quantum model here was small, so we did a small quantum model. If we compare historically, this would be a kind of, when we were in the perceptron, we had like one perceptron and was doing some kind of classification. But then there was this generalization of having a multi-layered perceptron in the 80s, and this one 1980s, and this was and this this was sorry about and this was a way of having more complex data and infinite, more and more complex data. And this was the invention of deep learning. This multi-layered perceptron was the invention of deep learning. Yeah, so we have a question from Theodonis that say quantum circuit is different for different data set. Exactly. For each data set, you have to come up with a quantum circuit, and I don't know how to make this quantum circuit. This is like something in the algorithm that is missing. It's still a little bit like this. When you do deep learning, you don't know exactly how to configure your layers, how many you need, how many, you don't know that. This is the same, but we have little guidance now how to design the quantum model. So, you can read the paper, you have like some hints, do that and do that, but there is no, we don't have a lot of guidance. And also you have like the quantum circuit. Now we were using only, simple entangling gates, like only CZs and CNOTs. And but actually there is, if you look at what we've been doing, in the hardware, they have like parametric entangling gates. Like for example, in ion traps machine, they have like the control phase gate that is 2 qubit gates with one parameter, and Google have this FSIM gate that is a 2 qubit gate with 2 parameters, and you have also the iSwap gate. So you have different kind of entangling gates, and here I even know less how to introduce this kind of gates in the circuit. So yeah, there is a lot of room of things to improve, to design here. So this is for no way. This is a very early work. I'm only happy because it ran, fully a small problem on a quantum computer, but there is still a lot to do. How to design the circuits and how to design the circuits and how to the whole algorithm, how to learn, how to do the predictor. There's a lot to do there, and to reach. So the algorithm has to be improved, and also we haven't shown yet any quantum advantage. So I'm reading here the question of Theodonis that say, instead of designing the circuit, could we redesign the way we create the data set? To come back to my previous question, we create the data set. Yeah, the data set, actually, you don't create them, you find them in nature, and you want to learn them. And maybe the question is the encoding function. Yeah, exactly. You can change the encoding function, the way you transform your vector, input vector, in angles of the parametric circuit. So this is something also that you can change, you can tweak. And for the moment, we choose like a very simple one. This is not by the only one to do there. So the full quantum model would be the encoding, how do you encode the data, how you what is the shape of your secret, how you ventilate the data, how you push the data in the secret. I mean, how you do the readout, the predictor, what is the function of the predictor, and then I mean, what's your loss function, and then how do you optimize the loss function? I mean, like, do you go on a stochastic gradient, or I mean, these are the classical optimizing stuff. But in quantum, you might need all the kind of optimization methods, and this is something that has yet to be designed. For the moment, the optimization methods don't take into account stochastic function and either quantum functions to quantum loss functions. So this is, there is a lot of work to be done. This is just like a first shot, I mean, at the problem.
Yeah, thank you. That's great, and you are answering all the question very elaborate way, and that was a very great, nice presentation. That was great, actually. Some questions are still coming.
Oh, you have a question, so let's go. I mean, I have time.
Okay, that's great. Then I think you can answer from Kameshwar. Pardon me if I did wrong pronunciation. Do we see overlap with reinforcement learning? Overlap with reinforcement learning. Yeah.
Okay, reinforcement learning. So actually, we could try reinforcement learning, but reinforcement learning, the thing is that, I mean, imagine that you have like what is the difference with I mean, supervised learning and reinforcement learning? Reinforcement learning is a kind of supervised learning, but instead of imagine that you present pictures of dogs and cats, and you say, okay, this is a dog, please learn from that, and this other one, this is a cat, and this is a dog, and so at some point, I mean, the learner is going to learn what it is because you are telling the learner this is a dog, this is a cat, so you still say the class. Reinforcement learning is a little bit like this. You say, or you present a picture, and the learner say cat, you say wrong, and they present another one and say dog, it's wrong, but you are not, instead of saying the what is the right answer to the reinforcement learning coexistence with QML. Yeah. So reinforcement learning, and it's not it's the way you optimize your function that is different. It's your loss function is different, but it's just you optimize the quantum function, so it's the same. It's just I mean, it's not it's the same. I mean, you have to come up. The algorithm is a little bit different, but it's not fundamentally different. I mean, classification with reinforcement learning, or I mean, it's possible. I haven't run it, but it's a lot less efficient. So I think if we can solve like simple problems first, reinforcement learning is probably a harder one, because you need even more. The optimization is even takes even longer in reinforcement learning, because you are not telling the answer. You're just saying it's wrong, it's okay, so I'm asking another question. With quantum circuit, could we use different topologies rather than the stack layers of deep learning? Maybe SOM self-organizing networks. Yeah, actually, yes. I mean, I have no idea. I mean, self-organizing networks could be like a good idea. I mean, I was doing these kind of things when I was doing distributed algorithms. So, I mean, imagination is king there. So, I mean, if you have an idea, just play with it. And this is how, I mean, the thing is going to come. I would say no idea is a bad idea. Just have to try to dig it, and yeah, and actually, I mean, I was surprised by the results we get there. So very, I had a very naive approach because I didn't know much about quantum computing. I didn't know either much about machine learning, so it was kind of very naive, my approach, but it works. So I like this sentence that by Mark Twain that say they didn't know it was impossible, so they did it. So I didn't know it was impossible, so I did it. So if you think that you have something, an idea there, and people tell you it's impossible, just try it. Maybe, I mean, you're going to succeed. Maybe, I mean, if you don't try it, you never know. So I encourage you to try things.
Yeah, that is great.
I think
Um,
Bamborde, organizer of the Fireside, was willing to say um, something at the end to wrap up the Fireside. I mean, if we are wrapping up now,
I think Bamberdo will end the session. And yeah, last few words very inspiring for young researchers or academian who wants to come in the QML field and quantum computing field. I'm not sure if is there Bamberdo to talk about or finish,
to
uh,
wrap up.
wrap up.
Uh,
Yep.
yeah, sorry
But
guys, I am back again. I was in the other end. Yeah.
great.
Did I hear you, Sakib, asking career advice to Joaquín? So asking what's the best, what would you advise to young people? I mean, in your early career, if they wanted to pursue quantum machine learning, is that what you were asking before I jump in?
Are you talking about me?
Yeah.
Yeah, I thought
So
you were asking a question to him before I. Oh, sorry.
Oh,
I realized I put
no, no.
my.
I was just saying that was a very last few words are very inspiring for young researchers to come in to play around the quantum machine learning and quantum computing. That was I was saying, telling or saying.
So I would say that is, I mean, you have this idea, I mean, machine learning, people say artificial intelligence, so it looks like something like very, a little bit scary, and you have like a Terminator attacking you, and you have like quantum computing saying like it's something like very, very hard. I mean, you have like to be like Einstein intelligence level or something to understand quantum computing. Is that I would say, I mean, don't let you intimidated by this kind of thing. It's not that hard, and just like to start doing things. I mean, I mean, small steps at the beginning, and then I mean, you take a bigger steps. But there is 4 small steps. It's it has not to be hard. I mean, you have like this and in English, you say like take baby steps at the beginning to just like go a little by bit. And since I'm just like saying quotes, I would take this Chinese one that say like 1,000 kilometer, I mean, journey always start by your first step. So just do your first step. And and this one could be like as easy, maybe. I mean, you can. I was suggesting you just go on dev.exa quite there, try the framework. You have an example there, and run it. It should take you, and then you have like run this iris data sets, and then you start tweaking it, and you do a little more complex things. And at the end, I mean, you do something that is worth a lot. Maybe you can, if you are doing a PhD or something, you can write a paper, or otherwise just like try something else and you put it on some repo and you can get a job. I mean, whatever is your motivation.
As long as we are talking about career advice, I have just last moment ask,
yeah.
are you still now working in execu.ai,
Yeah.
the slide?
Yeah,
Yeah.
I'm not hiring yet because actually I just launched the company less than 2 months ago. So I mean, I haven't raised money yet. I mean, so I cannot hire. Actually, I mean, I did have some people working like interns or low intensity interns, people that just want some advice. They want to I mean. So guidance, and I mean, I'm happy to just help people, and so this is for the
Well,
moment what I've been doing.
contributing to the project is the best, gives you the best shot for him hiring you. Huh?
Exactly,
Because
exactly.
it's like
So
you're proving yourself. This is what, and also for me, like this is one of the things that I'm inviting, people creating new open source projects, because I think there is more impact in your career contributing to something, a new project, than contributing to an existing project. Say, for example, you wanted to contribute to TensorFlow Quantum, for instance. If you tell me, oh, I contribute, I'll say, what impact do you have that Google couldn't, one of their developers couldn't have made? Whereas a new project, something like this, it gives you it gives you the opportunity to highlight yourself. So there is a bigger upside contributing to new projects like Joaquín's project. So that's why I really encourage those of you who want to get the certification stuff for this module to look at, especially those of you interested in quantum machine learning, to look at the project. So yeah.
so and yes, and I'd be happy to help. I mean, so you can just email me at joaquin.keller@exactquai.ai. You can find my email address as well on the web page. And yeah, so here you can go just on. Someone just already put it. I'm just writing on the chat. You go there and you will find everything to work, and my email address. So you can just like happy to answer any kind of question or help or any request.
I will also organize a Q&A because it seems some of you are not sure whether you should do a group submission or individual, and there is also the other thing whether you should do theoretical or contribution to open source. So I will organize a Q&A to, we go through the things to see the logistics of submitting this stuff, and then I can come up with criteria on how I will be judging the submissions. But impact is definitely one of the things that I will be looking, one of the metrics, how impactful your contribution is, So the newer the project, obviously the higher the impact for me.
Mm-hmm.
Because, we need more tools, we need more, the field is new, there is no like the thing. So, something like this, projects like this are the ones that you have more chances of impressing me with this than saying, other more like already established tools.
I would have like a kind of a joke one, but it's really true, is that if you are the first one to do something, you are the only one to doing it, so you are the best one. So
Yeah.
I mean, if you are the only one of doing something, you are the best one. If you are among like many people doing that, I mean, it becomes very hard to do the best one. So you are just going to be average. This is like the most common issue. But if you are if you are only three, I mean, the worst case is that you're the third best one, so it's still very good. So
yeah,
just
and even I also encourage
project.
those. Sure, I also encourage those, even if you are not submitting, contributing anything to do, give this project. It's very interesting. Give it a star so other people can find it. I'm sure the GitHub algo will do its magic so more people can find the project. So give it a star. Star it even if you are not submitting anything on the thing.
Oh yeah, thank you. Yeah, it would be great. Yeah, and the one thing also, I mean, is that there is something that surprised me in when I started doing quantum machine learning, And I would say, I mean, I had no knowledge of quantum. I had no knowledge even of machine learning, or I mean, very little in both. And I started doing that. Is that the field is so new, and it has been like most of the people are doing it. We are looking with their eyes. So they have, when they are new eyes, they see different things, and there is like so many low-hanging fruits. So when you get there with your eyes, they can see all these fruits there, and you can start getting all the what I say low-hanging fruits. So that's so easy to get new results because it's so very new. It's like, for example, Dijkstra. Let's look at very guy that invented algorithms like the Dijkstra algorithms. He just made this algorithm. He was with his girlfriend in a cafe, and they were just like tired. And he just came up with the Dijkstra algorithm in just like 20 minutes. I say it took me 20 minutes to do this algorithm, and now all my celebrity comes from that. It's an algorithm for searching in graphs, and because he was the first one to just thought about finding an algorithm to do a search in a graph. So now his algorithm has a name, the Dijkstra algorithm, but actually it's kind of simple algorithm. So this is the low-hanging fruit stuff of when you are new in some domain. And here in quantum machine learning, quantum algorithms, I mean, we are at the very beginning, so it's very there is this low-hanging fruit. So you can find really new results and make it I mean, a real important contribution to the field. And this is really nice. This is the reason. I mean, really that passionate me about in quantum computing is this stuff that everything is so new. You have so much to do, and then your contribution really matters. When you work on something.
Uh,
So really,
Sorry, is Bambordo or Joaquín is talking about anything? My internet somehow disrupted.
No, I can hear you. I was just listening to
yeah.
Joaquin.
We can
Yeah,
hear
yeah.
you. We don't
He's-
see your image, but we can hear you. Yeah. So I mean, it was very nice to have you guys, and I mean, with relevant question, and uh, I mean, I was happy there too. So I don't know if you have other question or remarks, and
No, that was
otherwise,
great. I think if anything, the audience got very inspired, to go and try out. And I like the fact that you said, don't feel intimidated, because one of the things that a lot of newbies they get is that, with all papers getting all over, archive every day, they think it's already been figured out. No, actually, even the people that you consider at the top of the field haven't figured it out. They are trying to figure it out. So do not feel like Joaquin was saying, just go out and try. Maybe you will find something else because you are thinking outside box. So,
exactly.
yeah.
When
So
I
thank you so
started, I
much.
mean, I was exactly like this. I was like, I mean, knew nothing. I was reading all these papers and I was impressed. I mean, I didn't understand half of what was there. And bit by bit, they say, but actually, they don't have anything. I mean, running. They're just trying. This is just the beginning. Let's say I want to try something as well. Let me try something. And actually, I tried and it worked. So, I mean, I just say, try things, and you will find results because they are there. So I think on this,
Fantastic.
yeah. So I think
That was really
this
very, very inspiring, and I hope to have you back again. Hopefully, some of them, those who decide to go and contribute, they can come in and present. Maybe they tried a different data set or contributed with something else, and I
yeah.
really look forward to that. So, yeah, thank you so much, Joaquin, for taking your precious time to be with us. You are now part of the community, so thank you so much.
Yeah.
Sakib, thank you also for taking on the challenge. It's not easy because I was looking for someone to moderate. So thank you so much for doing the moderation. And yeah, you want to make any final comment, Sakib, before we go?
Yeah, I am also very honored, and yeah, I was also very excited, and very great meeting was with Yakin. and that was very good session actually. and now I can feel proud about myself that yeah, I can do something.
Cool.
Okay, so thanks.
Okay, everyone.
Okay, bye. And I expect you to write me emails and start
Okay,
contributing
goodbye.
and
I think
everything.
Yakin and Bambordo.
Okay, so
Thank you so
bye.
much, guys. And thank you for those who had the time to tune in. And thank you to those who are going to watch later on YouTube. And I'll follow up about the certification stuff on the newsletter. Okay. So thank you again, Joaquín and Sakib. Have a good weekend, everyone. Bye for now.
Bye.